Welcome to this lecture on insect vector adaptations. Imagine you are a tiny creature trying to steal a meal from a giant, highly sensitive, and heavily armored monster. To survive, you would need highly specialized tools. In the world of medical entomology, insects are these tiny creatures, and humans are the giants. Today, we are going to explore the incredible evolutionary modifications that allow insects to successfully feed on blood and transmit diseases. Let us dive into how these tiny bugs become highly efficient biological syringes. Now that we understand the basic premise, let us look at what these adaptations actually are. Formally, insect vector adaptations are the evolutionary modifications in an insect's anatomy, physiology, and behavior. These changes do not happen overnight. They are developed over millions of years of an evolutionary arms race between the insect and the host. These adaptations specifically enhance the insect's ability to survive harsh environments, locate a suitable host, successfully feed on blood, and ultimately transmit pathogens. Without these specialized tools, an insect would simply be swatted away or killed before it could ever spread a disease. Building on that foundation, let us examine the first of the three pillars of adaptation: anatomical adaptations. These involve actual physical changes to the structure of the insect's body. The most critical example is the evolution of their mouth parts. Instead of standard chewing jaws, vector insects have developed highly specialized piercing and sucking mouth parts. These structures act exactly like microscopic hypodermic needles, allowing the insect to pierce through the tough outer layers of human skin and tap directly into our blood vessels with incredible precision. While physical tools are essential, they are not enough on their own, which brings us to physiological adaptations. These involve internal biochemical changes that happen inside the insect. For instance, when a mosquito pierces your skin, it injects saliva filled with natural anesthetics. This numbs the area so the host does not feel the bite and swat the insect away. Additionally, this saliva contains powerful anticoagulants. Normally, human blood clots quickly when exposed to air or injury, but these chemicals keep the blood flowing smoothly while the insect feeds. Beyond physical and chemical tools, we must also consider how the insect acts. This is the third pillar: behavioral adaptations. These are instinctual changes that dictate the insect's daily habits. A perfect example is the shift in hunting times. Many mosquitoes have adapted to hunt primarily at night, when their human hosts are asleep and defenseless. Furthermore, they have developed the behavior of resting indoors, on walls or ceilings, to avoid harsh outdoor weather and predators. Together, anatomy, physiology, and behavior turn a harmless bug into a dangerous vector. Let us visualize these adaptations in action by looking at this diagram of a mosquito bite. Notice the outer sheath, called the labium, which bends back as the insect lands. The sharp maxillae and mandibles are the anatomical adaptations, piercing through the epidermis and dermis layers of the skin. Down the center, the hypopharynx acts as a dual-channel tube. You can see the downward flow of saliva, which represents the physiological adaptation, delivering anesthetics and anticoagulants directly into the blood vessel. Simultaneously, the upward flow shows the blood being successfully extracted. Having seen how these adaptations work, we must ask, why is it so critical for us to study them? The answer is simple.
If we do not understand how an insect survives and feeds, we have absolutely no way to stop the diseases they carry, such as malaria or dengue. By studying their anatomical adaptations, we can design better physical barriers, like tightly woven bed nets that their mouth parts simply cannot penetrate. By understanding their behavioral adaptations, we know exactly when and where to spray insecticides, targeting them when they are most vulnerable.
This brings us to an important question. How do we actually measure the success of these adaptations in the real world? In epidemiology, we do not just rely on observations, we use mathematical models. We take the biological traits of the insect, such as how often it bites and how long it lives, and we turn them into measurable numbers. By doing this, we can quantify exactly how effectively an insect population can transmit a disease. This mathematical approach allows public health officials to see exactly which adaptation is the most dangerous and needs to be targeted first. To measure this, we use the vectorial capacity equation. Conceptually, this formula calculates the total number of new infections generated by one infected host in a single day. Let us break down the symbols. C represents the vectorial capacity itself. The variable m stands for the vector density, meaning how many insects are present per human. The variable a represents the biting rate, which reflects the insect's behavioral adaptations. Notice that a is squared, meaning any increase in biting has a massive exponential effect. The variable p is the daily survival rate, reflecting physiological adaptations, and n is the incubation period of the pathogen. The denominator uses the natural logarithm of p to represent the expected lifespan of the mosquito. Before we move on, let us see this with a concrete example. Imagine a village where the mosquito density M is 10. Their biting rate A is 0.5 bites per day. Their survival rate P is 0.9, and the incubation period N is 12 days. We want to find the baseline vectorial capacity. First, we substitute these values into our formula. We square the biting rate to get 0.25. We raise the survival rate to the power of 12, giving us approximately 0.2824. The negative natural logarithm of 0.9 gives a denominator of 0.1054. Multiplying the numerator and dividing gives a final answer of 6.7. This means one infected person will cause nearly 7 new infections every single day. Now that we have established a baseline, let us consider the threat of evolution. Suppose a genetic mutation occurs in our mosquito population that makes them much more aggressive hunters. This is a new behavioral adaptation. Because of this, their biting rate increases, but all other environmental and physiological factors remain exactly the same. We need to understand the mathematical impact of this single evolutionary change. Because the biting rate is squared in our formula, we should expect this behavioral shift to have a magnified effect on the overall disease transmission. Let us calculate the new vectorial capacity to see this impact. Our new biting rate A is now 0.8. We substitute this into the exact same formula, keeping the density, survival rate, and incubation period constant. First, we square the new biting rate, which gives us 0.64. Notice that while the biting rate only increased by 60%, the squared value has more than doubled compared to our previous example. We keep the survival probability at 0.2824 and the denominator at 0.1054. Completing the calculation gives a final answer of 17.1. This proves mathematically that a single behavioral adaptation can cause an outbreak to spiral completely out of control.
To wrap up our lecture, let us review the key takeaways. First, insect vector adaptations are incredible evolutionary tools that allow insects to act as highly efficient disease transmitters. Second, these tools span anatomical perfection, physiological trickery, and behavioral instincts. Third, by translating these biological traits into mathematics using the vectorial capacity formula, we can clearly see the danger they pose. As we proved, even minor adaptations can drastically increase disease spread. Understanding these concepts is your very first step in designing effective public health strategies. You have now mastered the fundamentals of insect vector adaptations.